Welcome to our channel. Today, we will provide an in-depth look at a ceramic material that has revolutionary significance in industrial applications, Zirconia Ceramics. Chapter 1. What is Zirconia ceramic? Zirconia, primarily consisting of ZrO2, possesses the highest mechanical strength and fracture toughness at room temperature among all major fine ceramics. During the heating and cooling process, zirconia undergoes phase transformations, which can lead to cracking. To mitigate this, stabilizers like yttria, Y2O3, are added during sintering. Most zirconia products are white yttria-stabilized zirconia ceramics. To meet more demanding operational environments, magnesium-stabilized zirconia, yellow zirconia, has been developed. Compared to yttria-stabilized zirconia, magnesium-stabilized zirconia exhibits significantly enhanced toughness. Chapter 2. Properties of Zirconia Ceramics. High toughness. Zirconia is more durable under impact and less prone to cracking compared to many other ceramic materials. High strength. High wear resistance. Chemical corrosion resistance. Melting point, 2700 degrees Celsius. Superior surface smoothness. Low thermal conductivity, approximately 2 to 3 watts per meter per Kelvin. Relatively high thermal expansion coefficient, approximately 10.3 times 10 to the power of -6 per degree Celsius. Chapter 3. Comparison between Zirconia Ceramics and Alumina Ceramics. If you are a mechanical design engineer or an equipment manufacturer, determining whether to use alumina or zirconia ceramics for your components depends on specific application requirements and working environments. Here are key factors and standards to help you decide which material to use. Mechanical performance requirements. If your components need to withstand high mechanical stress and impact, zirconia's high toughness and flexural strength are more suitable. If the components primarily require high hardness and wear resistance without significant mechanical stress, alumina's high hardness and abrasion resistance are excellent choices. Thermal performance requirements. Thermal expansion coefficient. If the impact of the thermal expansion coefficient is minimal or can be compensated for in the design, zirconia's high temperature performance provides more mechanical advantages. If the equipment experiences significant temperature fluctuations and requires a material with a lower thermal expansion coefficient to reduce stress and deformation, alumina may be more appropriate. Thermal conductivity. In applications requiring high thermal conductivity for rapid heat dissipation, alumina's higher thermal conductivity is beneficial. If thermal conductivity is not a critical factor, zirconia's lower thermal conductivity is usually not a limitation. High temperature performance. For components that need to operate at extremely high temperatures and maintain high strength, such as high-temperature sensors and gas turbine components, zirconia's high melting point and high-temperature strength make it more suitable. For components that operate at high temperatures but do not require extremely high strength, such as furnace linings and crucibles, alumina's high-temperature performance is sufficient. Chemical corrosion resistance. Both materials offer excellent chemical corrosion resistance, with no significant differences between them. Cost. Alumina is generally less expensive than zirconia. Chapter 4. Applications and product showcase of zirconia. I would greatly appreciate it if you could give this video a like and follow my channel. Thank you so much.